Okay. All right, I think I'm ready. Advent of Code 2024, Day 20. Race condition. The historians are quite pixelated again. This time, a massive black building looms over you. You're right outside the CPU. 2017, Day 24. Okay. While the historians get to work, a nearby program sees that you're idle and challenges you to a race. Apparently, you've arrived just in time for the frequently held race condition festival. The race takes place on a particularly long and twisting code path. Programs compete to see who can finish in the fewest picoseconds. The winner even gets their very own mutex. Okay. Nice. They hand you a map of the racetrack, your puzzle input. For example, it's unusual, right? Usually it's filled in better than that, but okay. I'll take it. The map consists of a track, including start and end, both of which also count as track, and walls. All right. When the program runs through the racetrack, it starts in the start position, then it is allowed to move up, down, left, right. Each move takes 1 picosecond. The goal is to reach the end position as quickly as possible. In this example racetrack, the fastest time is 84 picoseconds. Because there's only a single path from the start to the end, and the programs all go at the same speed, the races used to be pretty boring. To make things more interesting, they introduced a new rule to the programs. Programs are allowed to cheat. Rules for cheating are very strict. Exactly once during the race, a program may disable collision for up to 2 picoseconds. This allows the program to pass through walls as if they were regular track. At the end of the cheat, program must be back on normal track again, otherwise it will receive a segmentation fault and get disqualified. So a program could complete the course in 72 picoseconds, saving 12 picoseconds by cheating for the 2 moves marked 1 and 2. How's that compared to this? Oh, okay, that's here. All right. Or a program could complete the course in 64 picoseconds. All right. And this cheat saves 38. And this cheat saves 64, right? Going straight to the end. Okay. Each cheat has a distinct start position, the position where the cheat is activated just before the first move that is allowed to go through walls, and an end position. The cheats are uniquely identified by the start position and end position. Okay. In this example, the total number of cheats grouped by the amount of time they save are as follows. Okay. You aren't sure what the conditions of the racetrack will be like, so give yourself as many options as possible. You'll need a list of the best cheats. How many cheats would save you at least 100 picoseconds? Okay. Let's just do this really quickly here. Return, nope. Try again, return, and another slash, okay. Let's create this module. 2420 bake and run. Okay, I think we're ready. Let's get the input. 420. Okay, it's 141 lines. I imagine there's a start and an E in there. Hopefully just one of each. I see the S kind of buried in there. And I see the E here at the other end on a different line. Okay. I think we know what to do. We're going to use my position 64 stuff that I made a few days ago. Let's see, we're going to have a size 64, start, position 64, and an end, and then a path. I think that's all we need. Let's parse the maze. We should probably grab the test input as well. Copy. Cat test 20 text. Okay. And we'll say let lines equals AOC lib read lines test21.text, like that. Self size is equal to lines len and line 0 len. I have to say size, I think. Does that work? Oh, we have to pull these in. Okay. And then we say for row line in lines iter enumerate, for call ch in line chars enumerate. Standard boilerplate stuff I do for all these maze type programs, which I gotta add to my library. Say the position is equal to row as I64 call as I64. So we're going to say if ch is equal to the start, we're going to save the start position. Else if it's equal to the end, we'll set end. Otherwise, if it's this, oh, no, we can't do it that way. We have to, not else if. Right, because the start and end are included in the maze. We'll say self path insert pause. All right, so this should give us a maze. Oops, else if ch. I don't know how I left the ch off of that. Wait a minute. Oh, right, this has to be a position 64. All right, we can print the maze out. Make sure we have it correct. For row in 0 dot dot self size 0, for call in 0 dot dot self size 1. If let pause equals position 64 row call. If pause equals self start, print s. Else if pause is equal to self end, print e. Else if self path contains pause, print bang dot, sorry, and then println. Scoop says, did you say you wanted S and E to be part of the path? Because that's something you did in parse. Oh, you're right. Thank you. There, that's better. I'm sure I would have spotted it as soon as I printed everything out. Okay, so now here we'll just say self display. Oh. Print hash. There we go. Yep. And does that look approximately equal? I think it does. I think we're good. Okay, so now we just do a search. Okay, we're going to find, we have to find the path. That's step one. Even before we deal with all of this cheating stuff, we need to at least know what the path is. So, let's call it Q. I know I could use the pathfinding crate again, but I'm not going to. New from, we're going to go from the start. Cost of 0, self start. Visited, we need a visited hash set. And now we say while let some cost and position is equal to q pop front. They all have the same costs, which is why I can just do this with a q instead of having to deal with weighted edges. So that makes it easy. If pause is equal to self end, probably have to put a star in front of that. Then let best equals none. We'll set best is equal to sum cost. Break. Okay, and then we can print this out here. We don't, that's not the answer for this part, but at least we can say what the best is equal to. Otherwise, we're going to say if visited insert pause. If we haven't visited this location, then we want to get DIRs. Pull that in. I'll let new pause is equal to pause plus dir. If self path contains new pause, then we're going to say q pushback cost plus 1, comma pause, new pause. This isn't quite going to be what we need because we do need to save the path, but it should at least give us what we, the starting framework for getting the work done. 84. Is that even close to being right? 38, blah, 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 blah. Oh yeah, 84. Okay, so we got that correct. Now we need to save the path that we used. And that's going to take a little more work. Whoops. I don't know why I put a star there. Okay, let dist. We're going to have to save all the distances. Although this is a single. All right, I'm not gonna mess with what I know. Hash map, and it's going to be from position 64 to usize. And then back link is equal to a hash map of position 64, position 64. So here what we're going to do is, I think what we want to do here is say if we're not going backwards, right? Then we want to get the current distance, dist entry of pause, or insert usize max if, oh, we needed our new cost. If cost is less than entry, then entry is the cost, and back link insert new pause, comma pause. And that should give us the list. So we should be able to say println. Oh no, we have to reconstruct it from the end. Let mut, I guess we can call it pause, is equal to vec path. We'll call it the path, vec dec. From, and we're going to go from the end. Oh yeah, thank you, Scoops. And then we're going to say let mut current is equal to self end. We're going to say while let sum back is equal to back link of get cur. Then we're going to say path push front back. Let's call it next. And then we're going to say current is equal to next. And that should give us our return path. Let's just check that out. Println path is equal to path. Let's print out the length. Path len. Let's see if that's the same as our best. Oh, we don't have hash map. And okay. And now we have best equals none. Brilliant. I broke it already. Oh, this should be new pause. If the new position hasn't been. Oops. It's definitely broken. Do we have to do this? No. How did I break it? Oh, because I'm not, yeah, because I'm not even checking to see if it's on the path. If self path contains new pause, continue. I'm just going straight to the end. Okay, there we go. This is 85. Oh, because this takes 84 steps to get to the end. And so there's 85 because we include the start. I assume 3-1 is the start. Let's see if that's right. 1, 2, 3. Yeah, 3-1, then 2-1, then 1-1. Yes, 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 yes. Then 1-2, then 1-3. Okay, so I think we have the path. And now we need to figure out the cheats. Okay, here's what I'm thinking. And maybe this is the wrong approach, but we'll see. Let's say we have a path that looks like this. Let's do this. I'm doing it horizontally because it's easier for me to think about it. Like that. We can do this and then have a path like this. And maybe like this. Right? How about that? And we have, let's just mark all of these so I have names for them. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q. It's hard to see with all the everything in there, but I think I can figure it out. So we can do up to 2. So I'm thinking, here's what we'll do is we'll pair off all of the entries and then calculate the Manhattan distance between the two. And if the Manhattan distance between the two is, because we can do up to 2 milliseconds, we can check to see if this is the Manhattan distance. This is 1, 2, this is 3 apart. So we can't do that, but we can do this. This is just 2 apart. The same here, B to P is 2 apart. But we can also go to here, right? D to M should be possible, right? Because we're not there, and then we're here. That should work. Let's see if we can figure out how this will work. If we look at the path for I in 0 dot dot path len -1, and for j in I plus 1 dot dot path len, we should be able to compute Manhattan distance between I and j. If it's less than 3, then we have a potential shortcut. I think that's right. And then if the distance that we take, j minus I, is greater than that distance, then Oh, we only care about the ones that are... How many cheats would save you at least 100 picoseconds? All right. Why don't I see if I can print this information out first? If I can do that, then I can get this, right? Although none of these meet that criteria. Then add 1 to that shortened distance. We'll figure that out. And then once we're done with that loop, we should be able to filter out the ones that are at least 100. Okay. So we can say let dist is equal to path of I. I think I have distance too, yep. Path of j. And that gives me the Manhattan distance. So we can say if dist is less than 3 and j minus I is greater than dist, then let's create a new map. Call it cheats. Equals hash map from usize to usize. We'll say cheats entry of, and this is how much it saves us. Right, all we care is about how much we save. So it's this or default plus equals 1. I think that accomplishes what I'm looking for as usize. Okay. We don't have any output yet. So we should be able to loop over these now for kv in cheats. Println v ways to save k picoseconds. Do we have that information? Looks like it. Yeah. Okay. So right now, all we care about is the ones that are over. Oh, and unfortunately, we don't have an answer to this one, right? But we can compute this, right? We can say there are 5 cheats that save at least 20 picoseconds. So we can just write a little thing here and test it that way. The output should be 5. So we can say cheats iter map picosecs and ways. Oops. Oh, we can do a filter map. Right? And we can say if we're going to, how many cheats would save at least that many picoseconds? So picosec is greater than or equal to 100. Then it's some ways, else none. And then sum that up. Well, will this give us 5? Nope, not if I have a typo in my code. I thought I closed this. Oh, I didn't. Else none. Oh, I forgot this here. Okay. I have to deref picosec. Okay. Oh, I have to I have to reference it up here. Okay. Well, I'm going to get rid of that anyway. It says 0. Okay, so I have a bug in this. Oh, by greater than 100, right? I want to change it to 20. Greater than or equal to 20. And there's 5. Okay, so this line is correct. We can get rid of this, and we can switch from 20 to 100 and pull in the real code, or the real maze. Input 2024 20.text. It's not fast. It took almost a second, but we got 1426. Is that right? That's the right answer. Huzzah. All right. What does Clippy say? Oh, right. We're no longer using best. We don't need to know how long it takes to get to the end of the maze anymore. Okay. And then Clippy likes it. Gets this. Git commit. Oh, git add source. M 2024 day 20 part 1. All right. Let's take a look at part 2. The program seemed perplexed by your list of cheats. Apparently the 2 picosecond cheating rule was deprecated several milliseconds ago. Oh no. Old news. The latest version of the cheating rule permits a single cheat that instead lasts at most 20 picoseconds. Oh. Now, in addition to all the cheats that were possible in just 2 picoseconds, many more cheats are possible. The 6 picosecond cheat saves 76 picoseconds. Because this cheat has the same start and end positions as the one above, it's the same cheat, even though the path taken during the cheat is different. Okay. Cheats don't need to use all 20 picoseconds. Cheats can last any amount of time up to and including 20 picoseconds, but can still only end when the program is on normal track. Any cheat time not used is lost. It can't be saved for another cheat later. Okay, well that makes it a lot easier, right? You'll still need a list of best cheats, but now there are even more to choose among. Here are the quantities of cheats in this example. It saves 50 picoseconds or more. Okay, so we can actually use the example now. Oh, yeah, but he doesn't give us a total. But we can still print it out. Using the updated cheating rules, how many cheats would save you at least 100 picoseconds? Is this just changing a single number here? If I change this to 20 and rerun it, it gives me a bigger number. Oh, no. I said less than 3, right? Yeah, I said less than 3, so it should be less than 21. Okay. 1,697,000. All right, yeah. Hey, that's the right answer. Okay, but it's under part 1. Okay, so let's refactor this. Refactoring number 1 is we're going to use part 1 to calculate this path. And we're going to save this path in here. What do we want to call it?